예, 예, 예. 예. 네, 네, 네. 네.
그 트랜지스터의 그 전류 이대 베타 값이잖아요.
네.
그 실제로는 그게 막 베이스 전압이나 이미터 전압이 달라진다고 해서 달라지는 거 아니에요?
그렇죠. 예, 보유값이라고 하죠.
고유값이 근데 시뮬레이션 할 때
네.
그 베타 값이 그 전위에 따라서 달라지는 이유가
아, 그거는 이제 세츄레이션 리전하고
네.
그다음에 액티브 리전에서 달라요. 액티브 리전에서 픽스고 세츄레이션에서 달라져요. All right. How are you doing? How are you doing? It's okay. Not too bad, right? Not too bad. All right. Let's move on. So, I'm thinking to hold the final exam on December 10th. How about that? Please take a look at your calendar. December 10th or 12th? Which one do you guys prefer? 10th. Please raise your hand. 12. Half. Again, 10th. $12. Sounds fair. 12. Confirmed. Okay. All right. Let's move on. So last time we have learned about the area inversion charge density, right? So if we apply VGS higher than V threshold, we will have inversion layers that makes area charge density. Is that right? Yes. But here there is an assumption. What is an assumption? Here. With no VDS, right? VDS is equal to 0. Okay? In that case, the channel is formed due to inversion layers, right? That is all, right? And we can calculate that with Q inversion, right? And here, what is epsilon here? Epsilon is vacuum permeability, which is E naught times E of R, right? What is E of R? Relative permeability, right? Relative permeability. Now, when it comes to channel formed, we can view the channel as resistibility, right? Why do we say R on? What is on means? Inversion layer has been formed. That's why we say R on. Okay, R on. So here, the resistivity, which is rho times L over the inversion layer thickness, which is T inversion, times width, right? Width. So here, Qn times T inversion is equal to Q inversion, which is equal to Cox times VGS minus V threshold. So if we plug in this expression here, Q times N times T here, we can express R on in terms of VGS and V threshold. So from this equation, you can see that R on is proportional to what? Inversely proportional to 1 over VGS times V threshold. Okay? Oh, by the way, I forgot to say something. So here. If VGS is greater than VTH, we call the specific VGS as overdrive voltage. Overdrive voltage. Hey teacher, why do we say overdrive? What does over means? VGS greater than V threshold. That's why we say over, okay? Or greater, whatever you want to say. And I said the MOSFET is 3-terminal device. And what is the role of VG? VG is like a controller, right? Controller, right? VG is controller, and so that if you control VG, then what is going to happen? Current flows from where? Source to drain, right? Source to drain. So you can view VG as some kind of car handle, okay? Car handle, right? So you can adjust parking to drive when you drive a car, right? Right? So that's why VGS role is to let the current flow in the transistor. So we can view VGS as what? Car handle, right? So when you drive, you use the stick, right? To control the car. So that's why we say drive. Okay? Drive. You are driving your transistor. That's why we say overdrive voltage. Okay? Overdrive voltage. What is overdrive voltage? As soon as you hear these words, VGS is greater than V threshold. Okay, that is called overdrive voltage. In that case, you are in the driving mode. Driving mode is equal to current flows in the transistor. Okay, what is parking mode then? V threshold is less than V threshold. VGS is less than V threshold. Therefore, no current flow. That's parking mode when you drive a car. Okay? You got it, right? You got it. By the way, you're so hot. I know why. Because your passion towards learning is so hot. That's why. Right? All right. Anyway, R on is inversely proportional to VGS minus V threshold. So now we can see that if VGS minus V threshold increases, what is happening to R on? R on decreases, right? What does that mean? Then ID decreases, increases in the transistor. Increases. Okay? And this is called overdrive voltage. Overdrive voltage means the transistor is ready to conduct the current. Okay, that's why we say on. Okay. Now, let us talk about MOSFET channel potential variations. Okay, MOSFET channel potential barriers. Okay, so here, let us take a look at this first graph. Okay, first graph is V of Y versus channel distance Y. Okay, channel distance Y. So this B of Y is called channel potential. Okay, channel potential. This is the potential. This is the potential with respect to the distance, channel distance. Very, very straightforward. So please guess. And near the source, what should be the channel potential? Of course, 0, right? 0. Right? 0. What about here, near the drain voltage? Because the source is grounded, right? That's why. What about near the drain side? Of course, it has to be VD. Okay, VD. Okay, so at this point, what is the value? VD minus BS, which is VDS. Okay? Sounds good, sounds good. Now, let us calculate gate channel potential difference. Okay, gate channel potential difference. So what is this? So VG minus V of Y. Okay, V of Y. Okay, so at this point here, since V of Y is equal to 0, what about here? Of course, V of L is equal to V ds. Is that right? So now, what is the VDS? VD, right? Since VS is equal to 0, right? I'm talking about channel potentials. So now, what is the voltage here? VG minus VD. Is that right? Yes. Yes. Of course. Are you with me? Yes. Yes. There's good, right? There's good. Don't get confused. Okay? There is nothing you need to be confused. Okay? So now, let us talk about what? Why the title is maximum output impedance. It's nothing to do with impedance. I'm talking about the current ID. Okay? So you see that the channel potential varies with position along the channel. But unlike this case, the Q is different, right? So here, VDS is equal to 0, right? Here, in this case. But here, VDS is non-zero. Okay, VDS is non-zero. Therefore, there is Q inversion expression becomes Cox times VGS minus VTH. We gotta deduct channel potential as well. Okay, channel potential as well. Before, we never had any channel potential, right? Why? Because VDS is equal to 0. But here, VDS is non-zero. Therefore, we have one more term, which is VC of Y, which is channel potentials. So this is total inversion charge. Okay, and ID is equal to the width of a transistor times Q inversion of Y. What is this? V of Y. Velocity of the carrier. Okay, this is not voltage. Okay, velocity. Okay, so V of Y, which you have learned in chapter 2, is equal to what? You tell me. In solid, silicon, whatever you want to say. Mu of E. Yes, mu times E. You're true Yonsei genius. What is electric field? Electric field can be determined with voltage dV over dy, right? dV over dy. Oh, here. Okay. So mu of n is the electron field effect mobility. Okay. So under VDS, which is non-zero, the total charge expressions is different compared to when the VDS is equal to 0. Okay? So now, with this equation, with this ID, let us integrate both sides of the expressions. Okay? So here, we can integrate ID with respect to channel length. Okay? And we can integrate the right-hand side with respect to VD and VS. Okay? If we calculate this, we get these equations. Okay? Please do this by yourself. You can derive these expressions. Okay? So you see that ID is proportional to what? ID. So let me expand this expression. In that case, we get VGS minus V threshold, VDS minus VDS over this one. Okay? Now, please listen carefully. Okay? Please listen carefully. So let us compare the first term and second term. Okay? If VDS is so small, then which term is bigger? You tell me. Which term is more dominant between first term and second term? If VDS is so small, then which terminal is dominant? First term. So can we eliminate this part? Then can we say that when the region where VDS is so small, can we say this area is linear? Yes, of course. Yes, of course. Okay, so if we draw ID versus VDS, it is something like this initially. Okay, but then it becomes like parabolic. Okay, parabolic. But at the initial conditions, ID with respect to VDS is linear. Okay? So you've seen this before. Where? Vacuum tube amplifier. So when you learn about kindergarten physics, you learn about triode vacuum tube amplifier, right? So it looks like this. So this is triode vacuum tube amplifier. Okay, so we have here anode. So here's anode, and here we have something like cathode, and here we have a heater, and here we have control grid. This is triode vacuum tube amplifier. So in old days, back in 1950s, people used this triode vacuum tube amplifier as amplifying signals. Okay? So how it works? So if you use heater to heat up the cathode side, okay? If you heat up cathode is made out of metal, okay? So if you heat up with very, very high temperature, then what is going to happen? So what is going to happen to the cathode side? It emits electrons, okay? It emits electrons when the cathode becomes super hot. Okay, so when you take a look at the vacuum tube amplifier, you see like a bulb-like glowing, right? Bulb-like glowing. Okay? That is because heater is heating up the cathode side, and cathode emits lots of electrons. Okay, so these electrons is attracted by positive side, which is an anode. Okay, then which direction current flows? These directions. Okay, and why did I make a circle here? Because this vacuum tube amplifier is in vacuum condition. That's why. Okay, vacuum conditions. In the case, if you heat up the cathode side, cathode emits electrons. Okay, and now we have a control grid. Okay, control grid. What if you apply some bias, positive bias? then what is going to happen? The emitted electrons from the cathode side is going to which side? Some of the electrons goes to control grid, right? So that by controlling control grid voltage, we can control the flow of electrons, right? Oh, teacher, this is very similar to what? The operation of transistor. So this control grid is like handle of your car, right? Handle of your car. And the operation of vacuum tube amplifier is done by how many terminals? 3 terminals. That's why we say triode. Okay, triode. Instead of diode. What is di means? 2. What is triode? 3. That's why we say in old days triode vacuum tube amplifier. And if we plot the current flow, let's say I's of t versus, so here's anode cathode voltage. It's linear. Okay, linear. So here's linear with respect to V anode to cathode voltage. Okay, I told you every word have meaning, right? Yes? Questions? You? No questions? Okay. So here, this region where VDS is so small is linear, right? Linear region. So this operation of this region is called what? Please guess. Please guess. Yes, you can guess. Yes? What is it? The region where ID increases linearly is called triode. Okay? Because it behaves something like triode vacuum tube amplifier. Okay? So now we see that again, when BDS is so small, ID is proportional to VDS. What if BDS is not so small? Then ID is proportional to what? Negative parabolic, right? VGS minus VTH, VDS minus VDS square over 2. Okay? So, to be precise, if I draw carefully here, linear, and here parabolic. I's of D. Okay? Hey teacher! So here's VGS minus V threshold. What happens if VDS is greater than VGS minus VTH? Please guess. What is going to happen? Or what? If VDS great, yes, stays constant. Okay? Stays constant. Something like what? I IC versus VCE, right? Very, very similar, right? Very, very similar. So we call this region as triode. Here we say saturation. Why do we say saturation? Because current has been saturated. Therefore, the current behavior shows constant. That's why we say saturations. Okay? Sounds good, right? Sounds good. So now, for a fixed value of VGS, okay, constant VGS, ID is parabolic function of VDS. But to be precise, in this region, is linear. Okay, but then becomes parabolic. Okay, parabolic. And you see that ID reaches a maximum value at VDS is equal to VGS minus VTH. But then the curve stays constant. Okay? Curve stays at constant. And now, in order to find the maximum value for this, what do we have to do? This is what? Quadratic equation, right? In order to find the quadratic equation's maximum, what do we have to do? We gotta find what? The point of reflection, right? Point of reflections. Where does point of reflection occurs? At the maximum. So this is the this is an example of quadratic equations. Okay, and with that, the slope here and there is different, right? Why? That's why we say point of reflection, right? Reflections. So we gotta find what? The derivatives. Where the derivatives is equal to 0, right? In order to find the maximum value for this curve. So let us do that. Okay, so here partial derivatives of ID with respect to VDS is equal to mu and C ox W over L negative half. Welcome to electronic circuit 1. Plus mu and C ox W over L VGS minus V threshold minus VDS over 2. That is equal to 0. Okay? So, if we tie this first term and second term with mu and C ox W over L, we get VGS minus V threshold minus VDS. Is that right? Yes. Yes. So now, since is this non-zero value? Or 0, it can be 0. No, it is always positive, right? Always positive. Always greater than 0, right? So, this term has to be equal to 0. So, in order to find the maximum ID, VDS has to be equal to VGS minus V threshold. That's why we see that at this point, ID max occurs. Okay, ID max occurs at this point where VGS minus V threshold is equal to VDS. Okay? So now, with that in mind, let us plug in BDS expressions here and there. Okay? Then we get ID max as these expressions. Okay? Now, somehow BDS has been eliminated from the equations. Okay? BDS has been eliminated. So now, with that, if we plug in ID versus VGS, it looks like this. Why? Because ID is equal to half times mu n C ox W over L BGS minus B threshold square. Quadratic equations, non-linear equations. Okay? So now let us plot. Oh, that's okay. Yeah. Anyway, there are two types of curves. Okay? It is very similar. IC versus, in this case, VCE. Okay? What about here? In BJT, IC versus VVE. Okay? VVE. IC versus VVE is exponential. But here, ID versus VGS is quadratic relations. Okay? Now, let us talk about the inversion layer pinch off. Okay, pinch off. So now, please take a look at here carefully. Okay? So, the drain side is N plus. Okay? What about substrate? P minus, right? So if you apply positive bias to the drain side, what is this? What is this? So if you apply positive bias to the N plus side, then what can we view? The substrate and the drain side. Please tell me. You tell me. And the substrate is grounded. Reverse bias of diode. Can we say that? We are applying positive bias to the cathode side, which is N plus. Then the relationship between the substrate and the drain side is reverse bias condition in diode. Okay? Then, typically, what is happening? When we apply reverse bias to the diode, what is formed after that? What is formed at the junction? Yes. Great. So let me compare BJT and MOSFET. Okay, for the BJT NPN transistor, we have a depletion region under reverse bias, or the bias is equal to 0. Okay, and BJT. So here's base and collector, and here's depletion region, right? And what is happening? There is a electric field, and here's N plus. And what is this? The minority carrier concentration profile, right? Something like this, right? Linear, right? Why do we say linear? Even though it is exponential, but the base width is so narrow, right? So can we treat this as linear, right? And what is this electric field doing? Electric field is what? Sweeping electrons to the collector side, right? Let's see what is happening in MOSFET. So here we have here's the drain, here's source side, here's drain side, N plus, and here plus 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 plus, negative and negative and negative. Okay, and here you are applying VD. Here's positive, negative. Okay, so now here's source side. Okay, initially the electrons concentration is something like this. Okay, initially with this is VDS is equal to 0. Okay, but then under VDS is non-zero, then electron concentration profile looks like this, right? So electron, 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 something like this. Oh, teacher, I can see these are very, very similar. Okay, and there is a electric field as well. What if VD increases? Then what happens to the depletion width between drain and the substrate? What is happening? What is happening? Increases, decreases. Increases, decreases. Increases. So it pushes the electron concentration profile towards the source side, right? Towards the source side. So as VD increases, the channel becomes shorter and shorter. Okay? The channel length becomes shorter and shorter. Okay? What did I say about the channel length? Inversion layer length, right? Inversion length. Okay? So here, the channel length is what? What is the definition of a channel length? The physical channel length. The shortest distance between source and drain. Okay, that is called channel length. But then, after applying VDS, which is greater than 0, channel becomes shorter than its original length. Okay, that's why we say the point where the channel becomes shorter than its original length is called pinch off. Okay, pinch off. What is pinch means? Compressed. Okay, off means it's like a chopped. Okay, chopped. Okay, the point where, so pinch off is what? The point where channel becomes shorter due to non-zero VDS. Okay? You know what I'm saying, right? This will be on the exam, okay? So please, you gotta know what is going on, okay? You gotta know what is going on. All right? So now, with that in mind, what is happening if the channel becomes shorter? Then, do you guys expect ID versus VDS becomes something like this? Stays the same with increase in VDS? What is happening? The current increases slightly. Okay? This is exactly same as this principle in BJT. Okay? In BJT, what do we say? With increase in VCE, the current increases slightly. What do we say? Early effect, right? But please guess about the MOSFET case. The channel length becomes shorter and shorter as VDS increases. So by changing VDS, we can modulate, we can adjust, we can change what? The channel length, right? Therefore, in MOSFET case, we say channel length modulations. Okay, channel length modulations. Channel length modulation leads to slight increase in ID. Okay? Okay? Do not try to remember anything. You have to digest what I'm talking about. Okay? So here, in this case, by applying VDS, we can modulate the channel length. Therefore, there is a slight increment of current. We call that as channel length modulations. So you guys know the difference between pinch off and the channel length modulation, right? It's different, okay? It's different. What is the difference? I hope you know that. All right. Anyway. So here there is a slight increment of current. Okay, with increase in VDS due to the channel length modulations. Okay. So as we increase VD, we increase electric field, right? Electric field. What else? Here, what is going to happen? The number of charges in the channel varies. I'm asking you. No. The number of charges is already determined by VGS, right? Therefore, the number of charges remains the same, but the slope difference, right? As VDS increases. Slope here is steeper compared to this one. Therefore, the diffusion for the first case is greater than third case. Therefore, the current increases more. Current increases with respect to increase in VDS. Same as BJT case. Hey teacher, then why did you say the current flow mechanism in BJT case is diffusion? The number of carriers is made by diffusion. At where? At emitter junction, right? For the BJT case. What about second case? The number of carriers, the inversion layers are formed by VGS, which is electric field, right? Electric field. That's why MOSFET current flow is mostly driven by drift. Okay? This will be on the exam. I told you. Oh, with that, thank you so much. Peace out. I will see you guys on Thursday. 네.
프로젝트 관련 질문 드려도 괜찮아요?
프로젝트는
제가 이해한 게 맞는 게 거거든요. 핀치 오픈은 채널 X가 줄어드는 거를
핀치 오픈은 원래 오리지널 랭스에서
줄어드는
이게 줄어들어가지고 원래 이렇게 있다가 딱 끊어져 버린 거예요. 원래는 이 길이였는데 이게 갑자기 딱 끊어져 버렸어. BDS 때문에.
짧아진 거로 봐야
그 채널이 그러니까 그 채널이 오리지널 랭스보다 짧아진 그 순간 이 핀치 오픈.
짧아진 순간이요.
네.
그러면은 중간에 이렇게 그런 현상이
그래서
인해서
오프됐다고 하는 거예요. 그러니까 원래 이어져 있다가 소스와 드레인이 이어져 있다가 떨어져 나가버려. 그러니까 채널이 소스와 드레인을 연결을 하고 있었어요.
연결이 끊어졌다.
연결이 딱 끊어져가지고 오프됐다고 하는 거예요. 네, 그 순간을 핀치 오프라고 해요. 채널 랭스 모듈레이션은 BDS가 커지면 이제 이게 짧아지는 현상을 채널 랭스 모듈레이션.
짧아지는 이해했습니다. 감사합니다.
그래서 채널 랭스 모듈레이션이 변조를 한다고 합니다. 네.
강의실 이렇게 더워가지고 서울 들을 수가 없네요.
그래요? 제가 그러면 시설처에 좀 말을 해요. 에어컨은
해주세요.
네, 알겠습니다. 네.